Hey y'all, so I wanted to make this video just to be able to help those who might be redoing an electrical system for a boat, I guess technically for an RV or something like that as well, most importantly for a boat. And wanted to just break down different electrical systems and what I did for my boat, for my electrical system. I redid mine about a year ago now, and just now making the video, which is normal for me. But but yeah, just kind of want to run through a bit of the schematic for how the current's going to flow, where it's going to go through, what are going to be some main components, all that kind of stuff. So we'll pretty much just get into it. I'm going to use a bit of technical terms, well, some, but I'll try and explain them quite a bit. The main thing to understand is that on an off-grid system, such as living on a boat, um, everything is power conscious, and to understand that, you need to first look at what your power is going to break down into. We have volts, we have amps, and we have watts. For a lot of it, people seem to focus way too much on wattage when really they shouldn't. Watts doesn't actually mean anything. Watts is just our measurement of the amount of power consumed. It's not actually like the power applied. Um, it's just a way to measure it. It's almost like horsepower and torque, where horsepower is the rate at which power is achieved, and torque is the actual value applied, like the real amount of power. Whereas again, horsepower is just the rate that it can be done. So wattage is essentially a sum of voltage times amperage. So volts are the amount of current flow, and amps is the power applied for the current. So I say all that to say, really what matters is what kind of volts you're working with, which pretty much everything on a battery system is going to be 12 volt, at least over in the States. Europe is going to be 24 volts typically. And then you can even go up kind of from there, but mostly here it's going to be 12 volts, so that's pretty standard for a battery. And then you have the amps, and amps is everything. Amps is what you actually want to record. So if you were to say, like, hey, I'm using any kind of power application, so if it was a television or something like that, so I've got a TV right here, and it's just a 32-inch flat screen, like LED. And so it's like, well, how much does that pull? And most people are like, oh, well, how many watts? I don't really care how many watts. I really care about how much amps it's going to pull. Now, again, watts will be the volts times the amps, but really, I just want to know how many amps this thing's going to pull. And the reason why that matters is because you have to convert it from AC to DC. And whenever you do that, now you have power loss, and you're multiplying the variable. So in watts, doesn't really account for that. Amps actually does. So we're going to break this down on the grid here, and we're going to kind of look at how power is going to flow, what I did for my system. So let's see if I can. So bear with me here. I'll see if I can help walk through this a little bit better. But basically, this is my power grid. This is my power system. So I have two deep cell gel batteries, and I went ahead and upgraded to those from the wet leads. So I have wet lead acid. I used to have 4 wet leads, and each of them I think were about 100 amp hours. Which an amp hour is, how to even get into that, but it's the amount of amps that can be run per hour until it pretty much runs out. But then there's also another coefficient that goes with that, so amp hours even then aren't always what's used as the standard, but for the most part, that's how everything's rated, is in amp hours. So I've got two 250 amp hours, so 500 amp hours total, deep cell gels. Now the reason I went with deep cell gels is because versus AGM and lithium, deep cells were just best for my application. AGMs are great, but AGMs aren't quite as versatile as like gels. Gels can be in a little bit of more varied environments, so you can be much more hot environments, much more cold environments. They can shake a lot more and not be damaged because the cells are compressed in a gel-like form, so it gives a little bit of cushion. As well, they seem to be able to drain a bit better than AGMs. So I went with the deep cells, which theoretically you can drain way to a low percentage. I wouldn't go completely dead, but theoretically you can, and then be able to be recharged afterwards without damaging the cell. I normally keep mine pretty well topped off, but I've got 500 amp hours total. I ran mine in parallel because when you do in parallel, it multiplies the amperage versus in series multiplies the voltage. And again, being able to understand that volts is just the current, and since everything on my boat is a 12 volt, I wanted to keep it with 12. I didn't want to multiply the 24 because I don't want a 24 system. I want a 12 volt system. But parallel multiplies the amperage. So if I have, or adds the amperage, should I say. So if I have 250 amps on one and I run it in parallel, then now I have 500 amps instead of just the 250. So 12 volt together, 500. Now, the way that I ran this is I've got 2 house batteries, and then I have 1 start battery. The start battery is also a 12 volt, and where I put everything on here is these are 8D batteries, so these are massive batteries. They weigh about 200 pounds each, roughly, and they're pretty heavy. They're large. They're under the floor. I've got one down there, and then the other I actually put underneath the settee. I built a stand and put it in there. I'll see if I can include a photo of it. And then I have my start battery underneath here. And they're all pretty much wired together. I'll show you how they're wired here. But basically, the way this works is to run something in parallel, you do the positive to the positive, negative to negative. But the main positive that comes in off the main bus is going to go in battery A. It's going to cross over to battery B, and then the main negative actually comes out of battery B and then goes to your ground. So whereas in parallel you would do each one individually, or sorry, in series each one individually, this is in parallel. So that's how I did my battery setup. So I've got the house batteries tied together in parallel. They both run to my ground here on my engine, which is actually down on the engine base. I don't know if I'll be able to show all of this, but I'll try and get what I can. But I got them run down there. There's one negative for the house, and then one negative for the start battery, and then that last negative there goes to my alternator, and we'll get to that. But basically, we've got these two wired together, and then I also have a connection from the positive on, again, battery A to go to the start battery, and then there's this Victron controller here. Now what this is going to do is if my start battery is ever too low to start, or just running low in general, it will, this little controller here will apply the power from the house and send it to the start. You don't typically want to do this because these are designed to be deep cell. They're not designed to be kind of like high efficiency for dumping huge loads at a time, whereas a starter battery is designed to have the capacity to be able to dump a massive load to like start an engine. These can do it, but it's not very healthy for them. But in the instance that it needs to, this will essentially steal from the rich and give to the poor, and allow the house the house battery to help the starter battery to start the engine. Going to the actual engine itself, it's a Perkins 4108, and it's got a 100 amp hour alternator onto it. Now that that alternator is going to be grounded to the motor, as you kind of saw in there, but then it's also going to run to my tachometer. So I've got a tack plugged to my alternator rather than going to the actual clutch on the flywheel. It's just simpler that way, and that's the way it was designed to do, which is pretty common on diesel motors, to be honest. But yeah, so my alternator is going to charge, send the charge, should I say, to the main panel here. And this is going to then send it back to the house battery. But then as well, this is also plugged into my main bus, which is where we get pretty much everything is going to go back to the main bus. And the main bus eventually also goes to the main house battery. Goes through this main fuse, which I have, which is actually right here. You got this main fuse. This goes down to the house A and then goes up and around and connects to my main bus, which is back there. I'm going to try and keep it on this grid because this makes a whole lot more sense than that mess that's up in there. Even after redoing it, it's still pretty messy. So the summary is that the alternator will charge both the starter battery, and it will charge the starter battery because it's connected to this main switch, which is connected to the starter battery, but it's also connected to this main switch, which is connected to the main positive bus, which is connected to the house battery. So it charges both. And it's a smart regulator on here so that it doesn't send too much of a charge to overcharge the house. This is what I'm mostly concerned about, is keeping this regulated. Also the start battery too. Then we also have our other panel here, which also, like this one, goes mainly to the starter battery. This is more for the house. This is more for the starter battery. So that's just charging that comes off the alternator. That's how I can charge my house from my alternator. My main source of charging for these batteries is going to be split between, if I need, the battery charger, which is a 60 amp 3-stage battery charger by Victron. It's that right there. But as well, it is mostly going to be from my PVs, which is my solar panels. Now again, this is where I go back to solar panels and go back to the statement of amps versus watts. Most people, when they talk about solar panels, most people talk about how many watts they're getting from solar panels. Kilowatt hours, that is helpful, but at the same time, like if I were to say like, oh, I've got this massive 500 watt solar panel, but it's an old solar panel and it's pushing high voltage and very little amperage, then actually it's not worth anything. And if you look at a lot of solar farms that they're using out in these big fields and stuff in different states, a lot of these solar farms have actually trashed a lot of their old panels and are replacing all the panels because the old things are just worthless. They don't pull any efficient amount of amperage, any real power being applied. It's just high volts, low amps, which shows an empty wattage, a high wattage. That doesn't mean anything. They're not very efficient. Also, they're kind of running this series where if you get just a little bit of shade over part of the panel, the whole panel is pretty much shaded. Even though half of it's not, it acts as it is. Not very helpful at all. So being able to have new panels, new technology that can supply a heavy load, so high amps, it's called IMP, then that's what you're really after. And so what I have on my solar panels is essentially they're 220 watt panels. Again, I don't really care because the IMP rating is what matters. Each panel is typically bringing in, well, at max, each panel will bring in 13 amps. That's quite a bit of amperage from a small solar panel. When I say small, it's fairly decent size. But at that rate, I'm essentially getting about 55 amps off of 4 solar panels. 55 amps is a lot of power. That's a lot of power coming in that's free from the sun. It's efficient, and it fills my batteries pretty much in just the first couple hours of the day. So for the most part, I never even have to use my Victron battery charger. My Victron battery charger, which runs off a 120 volt system, that thing will push 60 amps at max whenever it's in bulk state. 60 amps is quite a bit, but that's only 5 amps more than my freaking solar panels do for free. And I don't have to worry about running a generator to supply the power load and all this kind of stuff. Like, no, it's just free coming in from solar. So the main thing about solar panels and the main thing about bringing in power for a lot of people that use solar panels is look at the IMP. Look at how many amps it's actually bringing in. That's really all that matters. I care less how many watts. A lot of people say watts and blah, blah, blah. And then they have these voltages that are bringing in like 26 volts and stuff, which means it's only bringing in maybe 2 amps. Like, what are you going to do with 2 amps? That's stupid. So, anyway, the main thing is looking at an IMP for a power grid if you're going to go with solar. And then each one is going to need to be run through an MPPT charger, which is a control charger. The way that I did mine is each panel is run individually to an individual MPPT Victron smart charger, which from there then goes to my positive negative main buses. I use them individually because I wanted to be able to monitor each one. I know you can program these with Victron and you can kind of tether them into a network, but it's a little bit easier to be able to understand if one is having a fault, you can isolate it and you can change that out versus having them all tethered together. So I'll show you kind of what I have really quick here. I keep it in my aft stateroom. But these are my solar MPP chargers. I went with the 120, which means that it can do 100 volts or 20 amps. And again, since each of mine are going to be 13 amps each, I had to get one for each. If I had an IMP of like 6 amps, then I could put, 3 of them on just one of these, but because I have high amperages, I need to have one for each. And Victron makes different ones. They make like a 120, 30, they make a 250, like 50 or whatever, but I wanted to do individual anyway. And then I went ahead and labeled them for the port, forward port, starboard, aft starboard, all that kind of stuff. So they're coming in from my solar panels, and then they're going to go back to my main bus. So, generally, what these will do is they'll bring the power in from the PVs, and they'll essentially do it in 3 phases: bulk, absorb, and float. Bulk is the batteries are low, and they just need a ton of amps to charge them back up. So it takes the max amount of amps that the sun will give it, and it'll just bulk send it into the main bus, which will then send it down to the batteries and just charge the batteries like crazy. This is typically what you can program them. I programmed them to send it at 14 point, oh gosh, I don't remember the exact. It's written on the battery what you can do, but I think it was like 14.6, because you don't want to overcharge. That can damage the cells. So while it's charging until it gets to about 80% full, it's going to go in bulk mode. Once it hits about 80%, then it's going to lower the amperage applied and going to go down to absorb mode. And absorb will still let a bunch of power in, but it's going to reduce it to a more manageable state so that it doesn't overcharge the batteries. So absorb is typically about like half the efficiency. And then it finally gets into a mode called float. And float just means these are capped off. You can program the percentage, whether you want it to be, like 80%, 90%, 95%, whatever. You don't typically want to charge them to 100, but you want to, because you want to keep it within range. Too much charge is actually bad for them, but you can program it for whatever it is. But let's say we get to 90% and we're good there. And so it communicates with the smart charger and it says, hey, I'm at 90% capacity. Let's go ahead and just sit it here. So it goes into the float state, which essentially means that it's not really going to send any amps in. It might kind of trickle them in here and there to maintain at 90%. But as soon as it starts dropping 89, 88 or so, it'll kind of boost back up. And you're going to get that throughout most of the day if you have an efficient system. Now, I run as much power as I want to throughout the night. I'm not worried because I have more than enough amp hours and these batteries are really efficient. And so, I'm running typically an internet box. I'm running a computer with a monitor setup. I'm running my refrigerator, which is a 12 volt. I'm running television. I'm running lights, which is all milliamps because they're all LEDs. I'm running whatever I want. Like, I run stuff all the time. I never worry about power. Not anymore anyway. And even with that, typically, because I'm bringing in, again, like 55 amps or so in a good sunny day, I'm in float stage, like I'm charged within 4 hours of sunlight. Like by 11 o'clock or so, I'm back on float. Like I'm doing really well. So it's just about how many amps can you bring in off your solar panels. So that's my main way of charging. It's going to come from my solar. The other way I could do it if I really need to is the Victron battery charger. And the way that that works essentially is this guy goes through a 120 AC, and I switch it over to my generator. Instead of going through my inverter, it goes through my generator. My generator, which is here, is connected through the grid into my main breaker panel. The main breaker, I put it on the shore power, and that is what allows it to divert the power from the generator to supply the 120 volts for the 60 amp. And basically it just takes the 120 volts coming in, and it boosts the load essentially as a step-up charger to 60 amps, and it sends it over to the main bus, which then goes back to the battery. So it takes 120 amps in, breaks it down to 12 volts, or sorry, 120 volts, takes it down to 12 volts, goes to the main bus, then goes down to the batteries. And this is also a 3-phase, so it'll look and see how much it needs, bulk absorption or float, and it'll apply it as needed. Whenever I don't use my battery charger, which I've only used a handful of times, I really don't typically need to. In fact, the only time I really did use it is when I first got these, because they were brand new, so they needed to be charged fully and capped off. So I went ahead and did that. I didn't have these yet. I got these like the next week. So yeah, that's about the only time that I end up actually using that. Typically, I'll run off of my inverter, which essentially the inverter switches, like I've got a safety lock system, which is right here. So this is my main power. Got everything, DC side, got my 2 switches. So this is basically for the house batteries, start battery. I just wire them on 2 different ones. I really shouldn't have, because I could have had a whole lot more. I could have 4 instead of having just the 2. And it doesn't matter. And I have my 120. Now, for the 120, like I said, it either comes through the inverter, which is going to be this one down here, or comes through my main disconnect, which is my shore power, which is essentially my generator, which is plugged into a shore power unit. And the way that this works is when I flip one off, it's got this little sliding brick, which won't allow me to have both on at the same time. If I were to do that, you can blow your system. You're throwing a bunch of amps at it. If you had both on at the same time, too much. So it's just a lockout. So essentially off, on, flip, flip. That's how this is all wired. I know it's getting kind of confusing. I'm trying to keep with all of this here. This is also for my records, not just for y'all, but if anyone is looking at how to do a system, like this is kind of how I had it run. So anyway, so that's my switch between the inverter, which is a 3600 watt pure sine wave inverter. And the difference between pure sine versus others is when you invert power, essentially what you're doing is you have a power current, and you've got direct current and alternating current. And so direct is a straight current that's applied. So if you were to think of, I don't have a pen on me, but if you were to think of it like a straight line of current, that's direct. It's just straight voltage. And so the straight source. And alternating current is basically a current wave. So it pushes the power in peaks and it oscillates it. And so when you really think about it, getting really, really down to the gritty here on AC, it's not normally a straight, clean pulse. It's typically actually like microscopically, it's kind of like a straight push, straight push, straight push. It's kind of like plateaus power, gives power, plateaus power, gives power. Now this happens extremely quickly, so it kind of acts like a wave, but really it's like a power, or power, 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 and then drops power and then gains power. And that's kind of how it kind of works for AC. A pure sine is able to essentially streamline that on a very microscopic scale and give a clean application of power, a clean pulse. And so you don't have as much flickering. Most devices like pure power better than this alternating kind of like on-off janky power. And it's just a lot more efficient. There's less power actually lost. Now, in an AC system, you're always going to have power loss, but pure sine, you're going to have a lot less power loss, also less heat generated, which is power lost. So I went ahead and went with the 3600 watt pure sine, and the reason why is because my main breaker, my main disconnect, is a 30 amp breaker. And so again, volts times amps gives you your watts. And so if I have 120 times 30, that is 3,600. So I went with an inverter that can do the max amount of power that this can actually handle. I didn't figure there would be a reason to have less for my inverter. I wanted to have enough power. I never really use 3,600, but at least it's there if I want to. As well, my generator is a 30 amp generator, 4,200 watt generator, max peak 42 anyway. And so it's still keeping consistent with that 30 amps that will be able to come in here. Anything past that is going to blow the breaker anyway, so I won't really need it. So that's kind of where I've been at so far with power that's supplied. I can either get it from the shore, which is my generator, shore power. I can get it from my battery charger. I can get it from my PVs, which is my solar panel. Now, those are all different ways to be able to power or charge these batteries and power the system. The way that I monitor all of this is going to be in a shunt. And a shunt is just a way to measure the amount of amps that are being used without blowing a device. Because amperage is, again, just straight power. It's the load applied. It's heavy power. Amps is what kills anything more than anything else. Volts don't really. Amps is actually what kills. That's the actual power. So you can't just monitor amperage without blowing a system. If you were to take like a multimeter, which I've got one, and you wanted to check amps, most multimeters can't actually measure amps. The expensive ones can, but a lot of times even then they're still doing smaller versions of amps. And the reason why is because it's just too much power going through a meter. It would blow the meter. So you use something called a shunt. And a shunt essentially looks like that. That's my shunt. And so it's I think it's a 600 amp shunt. And so basically what it does is it has power coming in and then goes through and then power going out the other side. And it steps down the power without actually like reducing it, basically. And it monitors how much amps are being lost in this through these little wires, which go up to my battery monitor, or my system monitor, my Blue Sea system monitor, which is right here. Now this thing is nice because using a shunt, and you would get the kind of the right kind of shunt that this calls for, I can measure everything on here. So I can measure how many amps are currently being used right now. I'm drawing this much with my fridge and everything. And then I can go through my different settings, AC power. So I've got 120 volts coming off the inverter. Bilge status, tank status. So fuel tank, water tank. House, system summary, battery temps, so on and so forth. Again, tanks, DC power, start, house, everything, back to the main. And there's actually more that this can do. But this is all measured through the shunt and through the tanks that it's applied to. So this is how I monitor pretty much everything. Everything goes through my Blue Sea system. Which is able to be used because of the shunt, because the shunt is connected to the ground, which goes through the negative on battery B, which everything goes through. So anything coming in here, like how much power is coming in here, makes its way down to here, and then from there goes to the batteries. They go up through the shunt. The shunt then supplies it to the system monitor. So if I want to know how much power is coming in here, or is coming from the charger, or is coming from the generator, or whatever, I can always just look at the shunt because it all comes back through, or sorry, the system monitor comes back through the shunt. The nice thing about Victron is you can also use an app, a Bluetooth app, and look exactly what you're pulling in. That I'll do at times as well. But essentially, I'll be able to know, like, oh, hey, I'm getting power in, so I've got, I don't know, I'm bringing in 48 amps right now. That's great. And then it'll actually, what it'll do is it does the calculations for me and says, let's say I'm using 9 amps, okay? And I look at my Victron app, and it shows altogether I'm bringing in 55 amps. But I'm using 9 amps DC. Well, then what this will do on the system display, it'll show I'm bringing in 46 amps because 9 of the amps are actually actively being used into the system. So it subtracts that and says, hey, you still have 46 amps actively coming in. You actually have 55, 9 of it's being used. You have 46 still loading into the batteries. It's pretty nice. I can keep track of exactly where I'm at. Or like right now, I'm not bringing in enough amperage because the sun's gone down. If you can tell, it's pretty dark out there. So I'm not bringing in anything. So I'm actually just using 9 amps. Now, this is why I say amps is what matters, because amps is the actual amount of power that you're using and being applied. Amps on AC and amps on DC are different. And the reason why is because the voltage is different. The voltage is either 12 volts or 120. 12 and 120, there's a big gap in numbers. That's over 100 gap. Like, that's a big gap. So if you want to apply how many amps are being used, you have to actually do the calculation. And an easy way to do it is just multiply it by 10. It's a little bit technically more complicated than that, but round it, multiply it by 10. So let's say that I have my television here, this TV. Okay, that TV takes 25 watts, and it takes I think it's 0.2 amps AC. Okay, so 25 watts, 0.2 amps on a 120 system. But when that steps from 120 steps from coming from the batteries at 12 to then convert it, or should I say invert it, to 120, power is lost. And so you have to now multiply that variable. So really, instead of it being 12 amps, 0.2 amps AC, it's times 10, which means it's actually 2 amps DC. And everything gets multiplied that way. So, big example, microwave. My microwave is a 120 volt microwave, standard microwave. It pulls 12 amps AC. And people think, like, 12 amps, that's not bad. You've got a 30 amp breaker. You should be able to do that. No, it's 12 amps AC, which means when it hits my batteries, which is where it's getting the power originally from, it's pulling 120 amps AC. That's a lot of freaking amps. That's a lot of amps. Even with good batteries, I never run my microwave off of my batteries. I always switch it over to the generator, run it for the couple, 2 minutes that I need to microwave something, and then switch it back over to the inverter. I do not want 120 amps pulling constantly at batteries. Microwaves are crazy pull because it's not just like a starter cap where it just needs a quick load. It's a constant 120 for every second that it's applied. My air conditioner, I've got a 16,000 BTU central air AC system throughout the boat, and that uses 55 amps to kick off, and that's 55 amps AC. So DC times 10, 155 amps to kick that thing off. There's no way I can do that off my batteries. Technically I could, but it would be killing them. Not gonna do that. Now it runs at 12.5 amps or so. So that's a little bit better. But you think about all the time that you're going to run your air conditioner for, it might be a couple hours. So you're running 120 amps at DC for hours on end. No way it's going to work. So that's when I change back over and go to my generator. I pretty much use the generator for the microwave and for the AC/heater. It's an HVAC. Those are pretty much the only things I ever use. Or again, if I need a battery charger, but 55 amps coming off the solar, I don't need a battery charger anymore. That's pretty much my system. That's how I monitor everything. it all goes through the Blue Sea. That goes to the 3 different tanks. Well, I've actually got 4 tanks. I've got 2 water tanks. One's in the V-berth and one's back here. But the V-berth feeds down into the main, and the main goes here. This is a 100-gallon tank. This is a 90-gallon. So I've got roughly 200 gallons of water, and they're monitored by some floats, which I actually just replaced. And they'll send their signal up to the Blue Sea. Fuel, I've got a 90-gallon fuel tank, which is right below my feet. That also just replaced the sender. That goes to the Blue Sea. And then waste, there's a 25-gallon, or actually 28-gallon waste tank, Blackwater tank, that's sitting underneath me right now. I need to replace the sender in it, but ew, gross. I do not want to pull that sender out. It always reads full. So I pump out my tank pretty much 2 or 3 every other day or something like that. It's always pretty much empty because that's gross. Having a full, that's gross. Nope. I just pump it out. That's it for today. Hope this is helpful, and appreciate y'all stopping by. Lord bless y'all. Appreciate.